Hi, welcome to Land of Math. You're probably here for the probability video. Come on in. Hi, this is Todd with the Land of Math. In this video, we're looking at probability. Now, it's a little bit longer video. It's like 40 minutes long. So down in the description, I'll break down all the different topics that we're covering and like the times when you can find them. So if you're looking for something in particular, you can jump right there. If you're a parent or teacher and you're looking for some additional resources, I might suggest you check out this book right here, Probability for Middle School. You can get it on Amazon, Teachers Pay Teacher link. I'll put it in the description below. Now, odds are you're ready to roll, so let's get going.
Probability is the chance of something happening. You probably had a coin flip before and somebody said you have a 50-50 chance of getting either heads or tails. Now, what does the 50-50 stand for? Well, 50-50 stands for 50%. When you're talking probability, we either write it as a percent. So for example, our coin flip would be 50%, a fraction, which in this case is 1/2, or a decimal, which is 0.5. Now, how do you get 1/2 for your fraction? The bottom number in probability is all the possible outcomes. So in our coin flip, it's either going to be heads or tails. The top number, in this case 1, is the favorable outcomes. In this case, we're talking about heads. So there's a 1 out of 2 chance. If you have your fraction to make it into a decimal, all we're doing is just dividing. So we're going to take our bottom number 2, divide it into the 1. In this case, it's going to go 5 times or 0.5. So 0.5 is our decimal. And to get our percent, we would just multiply by 100 and we get 50%. The next example is a spinner with 5 sections. 2 of them are blue. We have a green, a red, and a yellow section. And the question is, what's the probability of getting blue? Now, you're going to notice that when we write or ask these questions, we'll have a capital P, which stands for probability, and the blue or whatever we're trying to get on the inside. This problem, we have a 2 out of 5 chance. You can see we have 2 blue, and there's 5 different sections. If we want to take this fraction, the 2/5, and write it as a decimal, you can see we divide it and we end up with 0.4. To find our percent chance, or the probability, would be 40%. These are all acceptable answers. Now, in this next one, we want to find out what's the probability of not getting green. We still have 5 sections. 4 of the sections are not green. So if you look here, we have our 4 sections that are not green, which is the 2 blues, the red and yellow, and those 4 along with the green represent all of it. Now, if we want to take this and write it as a decimal, we take our 4 divided by 5 and get 0.8. If you want to find it as a percentage, we just multiply it by 100. So 0.8 times 100 is 80%. You'll find that almost all the time we write probability either as a percent or as a fraction. In the world of probability, an event is the activity or thing that you're doing. For example, spinning the spinner is an event, just like rolling a number cube, or flipping a coin, picking a card, or playing a little game of rock, paper, scissors. Each is an event. We can model probability with a number line from 0 to 1. The 1 represents something that is guaranteed to happen, the 0 represents something that's impossible to happen, and then everything in between. So let's say we're trying to find the probability of rolling a 7 with this number cube. Well, there are 6 different things that can happen, but none of those 6 would be a number 7. So the chance that we could roll this number cube and get a 7 is 0 out of 6. And that would show that on where the 0 is on the number line. Now, if the question was, what's the probability of getting a number less than 7? Well, now there are 6 different numbers that are less than 7. 1, 2, 3, 4, 5, and 6. Out of the 6 different choices. And the fraction 6/6 equals 1. So on our number line, we would put over here where the 1 is. It's guaranteed to happen. If you roll every time, you're going to get a number less than 7. If we're trying to flip a coin and we're looking at the probability of getting heads, So we're looking for the probability of getting heads. Well, there's two things that can happen, either heads or tails, and only one of them was heads. So if we go to number this, it would be right in the middle. Let's say we're looking at rolling our number cube, and this time trying to get a 3. So we want to get a 3. Well, there's only one 3 on this number cube. And there's still the 6 different numbers on here, 1, 2, 3, 4, 5, 6. So we would have a 1 out of 6 chance of getting it. So you can see over here, this is the 1/6 spot. Finally, let's say we have a spinner with 12 sections. And 12 of the section, or of the 12 sections, 11 of them are red, 1 is green. So if I want to know the probability of getting red, well, 11 of the 12 sections was red. So you can see it's really close to the 1. It's not guaranteed to happen, but it's really a good chance it will. Theoretical versus experimental probability. Theoretical is what we think should happen based on the numbers. So for example, if we look at our coin right here, we have a quarter, it's got heads and has tails. And let's say we're going to flip the coin or toss this 20 times. And we want to know how many times are we going to get heads. Now, what we can do is this. We can take the total number of flips, in this case 20, and we'll divide it by all the different things that could happen. So it's either could be heads or tails. Those are all the outcomes. And when we do that, we get 10. And basically what we would expect, what we think should happen is we should get 10 heads, 10 tails. Now we know that doesn't always happen. Another way you could come up with this number is by using a proportion. So for example, on the left I have the fraction 1/2. The 1 represents all of our favorable outcomes, all what we think or is going to happen, in this case heads. The 2 represents everything that can happen, in this case heads or tails. And then the 20 in the lower right, those are all of our total events, or in this case, our 20 coin flips. So the question is, well, if we flip this 20 times, how many times would we get heads? And so there's actually a couple different ways we can get this. Now, the first way is probably the way I was taught, is what we call cross multiply and divide. And so what we can do is diagonally, whichever two numbers we have, in this case the 1 and the 20, we would just multiply those. So 20 times 1 is 20. So no big deal there. We divide it by the other number, in this case 2, and we get 10, just like we had earlier. I've seen people do this way as well. They'll take, in this case, since we have the two numbers on the denominator, they'll take the 20, divide it by the 2, that gives us 10, and then we take that number times our numerator, in this case the 1. And 10 times 1 is also 10. So you can do it this way, the cross multiply and divide method like above, or you could do the method below, kind of a little loop-de-loop method, if you will. Either way, you end up with 10. So let's say we have this one right here. We have a number cube. It's number 1 to 6. And I want to know what's the probability of getting a 3, and if we rolled the number cube 18 times, how many times would we get a 3? We take our total rolls, 18, divide by 6, because there's 6 different things that can happen, and we get the 3. Every number should occur 3 times. The number 1, the number 2, the number 3, the number 6. Each of them should occur the same amount. In this case, they should occur 3 times. So we would think the number 3 is going to happen those 3 times. Now, let's say we looked at a different method of calculating this, and we looked at our cross multiply and divide stuff. Now, if we look at this one right here, we would set up the same way. On the left is our fraction, 1/6. 1 is our favorable outcome, in this case the 3. The 6 is all the different numbers that could happen, 1 through 6. And 18 is how many times we're going to roll this number cube. So if we want to find the missing number, what we could do is one of the two methods we talked about earlier. The first one, what we could do is the cross multiply and divide. So what we could do is we could take 18 times 1, and that would give us 18. Then we would take that number and divide by the other number, in this case 6. And we do it, we get 3. We could also do our little kind of loop-de-loop method where we go 18 divided by 6, which is 3, times our numerator, or the number 1, and 3 times 1 would give us 3. So we would expect the number 3 to occur 3 times. Now, let's look at a different example. So let's say we have a spinner here with 5 equal sections. 2 of them are blue, 1 green. We also have a red and we have a yellow. So there's 5 sections total, 2 of them are blue. So let's say we want to know what is the probability of getting blue. And let's say we're going to spin our spinner 30 times. Okay. So if we were going to spin a total of 30 times, how many times would blue occur? We take our 30, divide by the 5 sections. So there's our 5 sections right there. And we would get 6. Each of those 5 sections should occur 6 times. Now, because there are 2 blue sections, we would take our 6 times 2 to get 12. And you can see right here how we broke it down. Each of the sections should occur, in theory, the same amount of times. So I would think if we're going to roll or spin our spinner 30 times, blue should occur 12 of the 30. Now again, is it guaranteed? No. But this is what should happen in theory. Now, if we're trying to set this up as a proportion, like we've done on some of the other ones, on the left you have the fraction 2/5. 2 is our favorable outcomes. There's 2 blue. The bottom is the 5, which is all the different sections. And then on the right, lower right, is how many times we're going to spin this spinner. So 30 times. So all you have to do is you could do cross multiply divide. If you like that method, you would go 30 times 2 is 60. Divide by 5, and you would get 12. So we would think blue would occur 12 times. You can also do our little loop-de-loop method where we go 30 divided by 5 is 6. 6 times 2 would be 12. So it works that way as well. Experimental probability is the actual act of doing the event. So for example, we talked about flipping 20 coins. So I have 20 quarters here. So we're going to take the 20 and we're going to do the experiment. We're actually flip them and toss them here. So we'll shake them up a little bit. And when we do this, we'll record the results. And what happened was heads only occurred 7 times. While on the other hand, tails occurred 13. So it's actually what we thought would happen. Our 18 times we roll our number cubes, we were looking at the number 3. And in this case, the number 3 occurred 4 times. So the experimental probability would be like 4/18. The number 2, for example, actually happened 5 times. So that one would be 5 out of 18. Remember, we thought each was going to happen 3. If we look at our spinner, what we did is we were spinning the spinner 30 times. Now, I'm not going to show you all 30 because that would be kind of boring. But once we did all 30, we recorded the results. And so the results were this. Red occurred a total of 6 times. Blue occurred 12 times. Yellow 8 and green 4. All right, now we're going to compare the theoretical and the experimental. So on the coin flips, we thought 10 out of 20 times we should get heads. When we did the actual experiment, it actually only occurred 7 times. So when comparing these two, our coin flip, the heads actually occurred 3 less times than we thought. The number cubes, we thought the number 3 should occur 3 out of every 18 times. Now, when we actually did the experiment, we actually rolled 18 number cubes. The number 3 actually occurred 1 time more. On our spinner, we thought it should happen 12 times, and sure enough, it did. So what our theoretical probability was and our experimental probability, they were the exact same things. A simple event is just one event. It's one tossing of the coin, for example, which would be a 1 out of 2 chance of happening. Or just one time spinning a spinner, we would have a 1 out of 4 chance of getting the number 4. Or just one time rolling a number cube, and we'd have the probability of getting a 5, 1 out of 6. All right, a simple event has just one event, but compound has multiple events. It could be 2 events, or it could be 3, or it could be 20. So for example, if we're rolling a number cube, or 2 of them, each number cube represents an event, and each one has a 1 out of 6 chance of occurring. Let's say we want to flip a coin or flip 3 coins. And for each of these coins, what we're hoping to get is heads all 3 times. Well, each event has a 1 out of 2 chance of occurring. Modeling compound events is a great way to show all the different possible outcomes when we have more than just one event. The first is the frequency table. So we have in this case, 2 quarters that we're going to flip. And we want to know what's the probability we get heads both times. So we start off by making a basic rectangle. And what we're going to do is on the left side here, we're going to have a quarter, and we're going to put down all the possible outcomes. So in this case, heads and tails. And then we're going to split this going across. We're going to draw a red line here, going across. Now, at the top of our rectangle, we're going to do the same thing. All the possible outcomes of this quarter would either be heads or tails. So we're going to use a different marker. We use blue in this case. And we're going to split going vertically this time, this rectangle, or this box. Now, going across here, with heads, we're going to fill in H's and all the boxes going to the right. And then we'll do the same thing with tails. Going down, we're going to do the same thing here with the blue H. So H is going down, and then T for tails going down. Now, if we're looking at the probability of getting heads and then heads again, so 2 events, so compound events, you see that we have a total of 4 different combinations possible, but only one of these 4 is actually heads. Now, in this next event, we have a spinner with 4 sections and a number cube with 6 sections. Now, we're going to do the same thing here. We're going to start out, we're going to draw a rectangle. Now, as we make the rectangle on the left side here, we're going to put all the combinations that are possible for our spinner. Now, we're going to use colors and not the numbers in this one. So going down the left side, we'll put a letter down for each one of these. So we've got like green and blue and yellow and probably like purple or pink or something. So we'll put all these down here. Because we have 4 different colors, we're going to make 4 rows. With our number cube, we have a total of 6 different things that can happen. So across the top, we'll put the 6 different outcomes possible, 1 through 6. And then we'll divide the box going down vertically. And so now we have 6 columns going in. Now, just like with the coin, we're going to take the B in blue here and go fill in all those squares going across. The same thing for the Y for yellow, same thing for P for purple, and same for green going across. And so all these boxes will be filled in. Now going down, we're going to take the red numbers and we're going to fill in the boxes. So for example, the 1 will go in each of these boxes going down, and the same all the way up to 6. So when you look here, if we're trying to get the combination of green and a number 6 on our spinner, the green, and on the number cube is 6, if we look at all these different combinations out there, there's only one spot on this entire grid that has that combination of a green and the number 6. Now, there's a total of 24 different combinations out here. So if we're looking for the probability of getting green and a 6, it's 1 out of 24. The next way we can model is something called a tree diagram. Now, if we go back to when we just did the frequency table with the 2 coins, you can see that there's a total of 4 different combinations possible. And when we're looking to get heads and heads, you can see we had a 1 out of 4 chance of it happening. And you can see each of those combinations there. With a tree diagram, we're still going to try to find the combination of heads and heads. So what we're going to do is in event number 1, what we're going to do for event number 1 is we're going to write down all the combinations that can happen in this first event. Now, all the combinations that can happen, or all the outcomes, maybe a better way of saying it, is either going to be heads or tails. So pretty self-explanatory there. Now, they call it a tree diagram. Obviously, I didn't name this, but I assume this is because it branches out. So when we get to event 2, so the first event was the first coin flip. The second event is the second coin flip. So what we're going to do is if we look at the first event where we got heads, and we ask ourselves what can happen in this next event. Well, we're either going to get heads and then heads again, or heads and then tails. And you can see how it branches out. Now, if we happen to get tails the first time, we could either get heads the second or tails the second. And what you can see here is 4 different combinations possible. If you follow the lines, it will show you each combination possible. So let's say you have 3 events instead of 2. So let's say we're going to try to flip these 3 quarters, and we're going to try to get heads all 3 times. Now, because there's 3 events, we couldn't use a frequency table because we only used 2 events there. So, but we can do this with a tree diagram. So that's what we're going to do here. So when we look at event number 1, which is going to be our first coin flip, we ask ourselves, what are all the different things that can happen, all the outcomes? And again, it's going to be either heads or tails. So it's going to be pretty straightforward. Now, as we start to branch out our tree diagram, we go to the second coin and we ask ourselves, well, what can happen? Well, if we get heads the first time, we can get heads the second time. You could also have this combination, heads and then tails. So right now you can see we have 2 combinations. Now, if we happen to get tails the first time, we could have got heads or we could have got tails again. So right now, after 2 coin flips, there's our 4 different events. But now we got the third coin flip. And so what we're going to do here is we're going to branch out from each of these. So let's say you had heads and then heads again. So now what could happen? So if we had heads the first time, heads the second time, the 2 things that can happen is either we're going to get heads or we're going to get tails. So what we're going to do is we're going to take that heads right there and we're going to split it out 2 ways. So there's the heads and there's the tails. What if we happen to get heads and then tails? Well, we either get heads the next time or tails. And so with each of these, we're going to branch it out with all the outcomes possible. Heads and tails. And finally, we could have tails, tails, and then heads, or finally, tails all 3 times. So you can see there's 8 different combinations here that are possible. So if I'm looking for the probability of getting heads, then heads again, so 3 straight times, that combination only happens 1 time, one of these little paths right there. So it happens 1 out of all the 8 different combinations. So our probability is just 1 out of 8, or 1/8 chance. Here's another example of modeling with the tree diagram. Let's say you're going to play some rock, paper, scissors. And you're going to play 3 straight times. And you want to be able to guess what your opponent is going to pick 3 straight times. All right, so what's the probability of that happening? Well, first of all, what you would do is on the first event, there's 3 things that can happen. The rock, the paper, the scissor. If you look in red, you can see they'll have each of those down. So you have a 1 out of 3 chance of guessing what your opponent's going to do. Now, when we get to the second roll, or the second rock, paper, scissor, again, there's 3 things that can happen. Rock, paper, scissor. So let's just say, for example, that you got rock the first time. Well, what could happen the second time? Again, either rock, paper, or scissor. So you're going to get one of these 3. Now you can see I've written this down in black. So it's either going to be rock, 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 paper, rock, scissor. Maybe if you get paper the first time, then you would get paper, rock, paper, 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 scissor. And the same thing if you get scissors the first time. It would be scissor, rock, scissor, paper, scissor, scissor. As you get to the third time, you're trying to predict the rock, paper, scissor. What you're going to do is, let's say, for example, you got the first one right. Let's say it was rock. And let's say the second one was correct, and it was also rock. When you get to the third pick, again, you've got 3 different options. It's either going to be rock, paper, or scissor. And you can see how we're branching out from this rock. So I have the rock, the paper, and the scissor right there. And I have those in blue. We're going to do this with each of the different ones. So if we got rock, paper, well, the next time is either going to be rock, paper, or scissor. So you get rock, paper, paper, or whatever. And that's going to happen on all the rest of these too. So whether you got paper, paper, then rock, paper, scissor, or whatever. And that's going to continue down. When you count up all these different, like the little, how they end, there's a total of 27 different combinations. So if you were trying to get, let's say, rock, 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 there's only one combination where you have those 3 events. And so you'd have a 1 out of 27 chance Another way to model probability or compound events is with an organized list. So let's say you had a quarter and this number cube or a die, and you want to model all the possibilities. What you could do is literally just write down in a nice organized list all the combinations possible. In your first event, the coin toss, you have one of two things would happen, either heads or tails. So what we're going to do is we're going to put heads down every single time and put down all the possible alphas or combinations with the second event. So heads 1, heads 2, all the way up to heads 6. Now, we could also get tails on our first event or the coin flip. So we would do the exact same thing. Tails 1, tails 2, tails 3, all the way up to tails and then 6. And then if we're trying to find out like a certain combination, like what's the probability of getting heads and a 4, well, it would be 1 out of 12. There's only one of those 12 that have that combination. Now, if we look at this one right here, this is our tape or our tree diagram from the previous example. And we're playing rock, paper, scissors. And so it's kind of the same thing here. We have the tree diagram with all the combinations, but we can make an organized list with this as well. And so what we have right here is our organized list. And what you're going to notice is the column on the left side, it starts with the red or the rock every single time. So here's like rock, rock, rock. And you can see that on the tree diagram right there. And you got rock, rock, and then paper, and then so on. So every one, like I did the rock always is colored in red, paper is in blue, and scissors is in green. When we get to the second column, you see that we start with paper every time. And then when we get to the third column, we're going to start with scissors every time. And so all we're doing is we're putting all these combinations down. And there's a total of 27 of them. Now, if you're looking for a certain combination, let's say you were looking for, I don't know, let's say rock, scissors, scissors. Well, you can see at the bottom of that first column, rock, scissors, scissors. Okay. Here we have, for example, let's say you want paper, paper, scissors, paper, paper, and scissors. So right there. So it's a great way to model or to show all the different possibilities. Modeling is helpful to kind of help kids see what's going on, but what we really want to get into is the math behind it, because that's going to save us time. So let's say we have these 3 quarters right here, and we want to find out what is the combination I can get heads, heads, and heads. So basically flipping a coin 3 straight times or 3 different coins and getting heads each time. So what we're going to do is we're going to look at each individual coin and the probability of that event occurring. So on this first one right here, we have a 1 out of 2 chance of it being heads. The second one's also 1 out of 2, and so is the third. All we have to do at this point is just multiply these together. So when we multiply our numerators, we get 1. We multiply 2 times 2, we get 4 times 2 is 8. So we have a 1 out of 8 chance. Now, you can go back and look at the tree diagram that we were using earlier for this. And you can see that there's 8 different combinations possible, and the heads, heads, heads is just one of the 8. So we can just do the math and kind of, the tape diagram takes a long time. It's good to see, but doing the actual math is going to make it a lot quicker and easier. So let's say we upped our game here a little bit, and we decide we want to make it 4 coin tosses. What's the probability we could get heads 4 times in a row? Well, the probability of this next coin is also 1/2. So we could just multiply by 1/2, and that's going to give us 1/16. So we would have a 1 out of 16 chance, or there's 16 different combinations, but only one of them is heads, 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 and heads. Now, this will work with other stuff. So let's say we have some number cubes here. The number cubes are each numbered 1 to 6. So when we look at each event, which would be each rolling of the number cube, each event we basically have we do have a 1 out of 6 chance of happening. So if we want to find the probability of us getting a 1 on all 3 of these, we would just multiply 1/6 by 1/6 by 1/6. And when we do that, we're going to get 1 over 216. So there's 216 different combinations possible, but only one of those 216 is 1, 1, and 1. Okay. And when we actually do it, we can actually see what's the chance of it happening. Not very good. So, because we only had 1 out of 216. So let's say you're playing Yahtzee. Again, we're using dice here. So each one has a 1 out of 6 chance. So let's say you're trying to get all 6s. Okay? And on your first roll. So there's only one way that's going to happen. But there's a total of 7,776 different combinations possible. Now, if we were trying to do a tree diagram of this, it would take forever. So this is clearly a lot quicker and easier. But there is 7,776 different things that could occur. Let's say we have this spinner, a die, and a coin flip. And we want to know what's the probability that we could get all 3 of these correct. So for example, maybe we're trying to get blue, number 6, and heads. So when we look at each event, we're looking at what's the probability of that happening. Well, the spinner, we have a 1 out of 4 chance. The number cube, or the die, we have a 1 out of 6. And the coin flip, we have a 1 out of 2. So all we have to do here is just multiply these together. So again, if we multiply all the 1s, we're going to get 1. And then when we multiply the bottom numbers, we're going to end up with 48. So we'd have a 1 out of 48 chance of getting all 3 of these correct. All right, independent and dependent probability. Now, the probability that we've been working with so far has actually been independent probability. And what that means is the odds or the probability of an event happening is not impacted or affected by any previous event. So for example, if I was going to roll this number cube, the probability I'm going to get a 5 is 1 out of 6. After I roll the number cube and I give it to the next person, they have the exact same chance of getting a 5, 1/6. The same thing would happen for like the spinner. I have 5 sections in this spinner. When I go to spin the spinner, I have a 1 out of 5 chance of getting yellow. Now, when the next person comes up, they would also have a 1 out of 5 chance. The odds haven't been affected at all. Same with a coin flip. Coin flip is probably the most famous of all the independent probability. Every time somebody flips a coin, you're going to have a 1 out of 2 chance of getting heads or getting tails. Your odds stay the same, exactly 1/2. When we're talking about dependent probability, what it means is you are dependent on what happens before you. If somebody rolls the dice, whatever it is before you, it's going to impact your odds. So we have a couple examples here. So we're going to start out with 8 tiles. 3 of them are green. Our goal is going to be, or we're looking at the probability of getting 3 green in a row. So we'll throw our tiles into our Pringles can here. We're not sponsored by Pringles, but Pringles, we're always available. And so when we reach in, our probability of getting green would be 3/8. Now, notice we put the green tile back into the Pringles can. So the first time I reach in, I have a 3 out of 8 chance. As I would get ready to reach in a second time, my odds are the same, 3 out of 8. And if I put it back in there again, it's 3 out of 8. This is an example of independent probability. My odds haven't changed. Every single time it's the same. And so when you look at the fraction, it's 27 out of 512. And that breaks down to about 5% chance of happening. Now, let's do the exact same scenario, same 8 blocks, still using 3 green. And what we're going to do here is this time, when we reach in and get a tile, we're going to keep it. We're not going to put it back into the container. So we'll take these, throw them in our Pringles can, would shake it up. Now, obviously, I'm probably cheating a little bit, but let's say when you reach in that first time, again, we're trying to get 3 in a row, your odds of getting green is 3/8. Now, as we get ready to reach in the second time, what we're doing is we're keeping the green one out. So our odds have changed. There's only 2 green left in our Pringles can, and there's a total of 7 objects. So the odds have become 2 7s. So let's say you reach in again and you get green. As you get ready to reach in the third time, there's only 1 green one left. And there's a total of 6 in there. And so now we would multiply these across. And what you would find is we're going to get the fraction. We're going to have 6 on top. And then you end up with, I believe it's 336 on the bottom. Now, if we convert that to a percentage, you're going to get something around 1.8%. And 1.8% is a lot less than the 5% that we had earlier. Now, both of them, the percents are low, but 5% is like 2.5 times greater chance of happening than the 1.8%. And you can see the math here. The top one is an example of the independent probability, and it was always 3/8. Dependent probability, you can see it changed every time. You're dependent on what happens before you. So for example, if we were trying to get green 4 times in a row, we would have a chance with independent, but with dependent, it would be 0% because we'd run out of green. All right, in this next example, we're going to use a fun-sized pack of M&Ms. Now, we're going to dump them out, and you're going to see that we have a total of 10 M&Ms. 5 of them are orange, 3 blue, and 2 yellow. So what we're going to try to do is calculate the probability of pulling out 3 straight blue M&Ms. So we'll throw our M&Ms back into our bag here. And again, we're not sponsored by M&Ms, but M&Ms, feel free to reach out to us. We'll talk. So we got our M&Ms. As we reach in here, now if we weren't looking and cheating like I'm doing right now, we would have a 3 out of 10 chance of getting a blue M&M. Now notice I dropped it back into the bag. As I get ready to reach in this next time, I would also have a 3 out of 10 chance. So we get ready to do the math here. You're going to see that the probability, again, this is an example of independent. The first time we had a 3 out of 10 chance, the second and the third time also 3 out of 10 chance. So when we multiply this all together, we have a 27 out of 1,000 chance of getting blue 3 straight times. Okay. Now, let's say we did this again, but now we're going to use dependent probability. So the odds are going to be changing. You're depending on what happened before you. So let's say the very first time you got blue, but you didn't put it back into the bag. So the probability in this first one is 3/10. So you have a 3 out of 10 chance of getting it, just like with independent probability. But as you reach in the second time, there's 1 less blue M&M. So now you have 2 M&Ms to pick from out of a total of 9. Now, if you were lucky enough to get blue the first and blue the second, as you reach in that third time, there's only 1 blue M&M left out of 8. And so what we would do is just multiply this straight across, and you're going to end up with 6 out of 720. So that's your chance of getting blue M&M 3 times using dependent probability. Now, that's kind of hard to compare those two, so we can write them as percentages. So this first one, the independent, you had about a 2.7% chance of it actually occurring. So 2.7% for independent probability. For dependent probability, what you're going to find is it's going to be around 0.8%. Now, just to give you a little bit of idea, the chance of independent probability is actually greater. It's actually 3 times greater than dependent. So dependent and independent probability are different. The main thing is dependent, your odds are constantly changing. Combinations are a lot like dependent probability. We have here 5 different cards: an ace, a 2, a 5, a jack, and a king. Now, combinations, I might want to know how many different combinations are possible. How many different ways can I rearrange these cards? You could also think of it this way: what's the probability you could guess what card or how I would arrange them? Now, if I switch to the jack and the 5, that's another arrangement. If I switch the king and the ace, that's another arrangement or another combination. So let's say you were going to try to guess what combination or what arrangement I would have. So you can actually pause it and try to guess here. So I would take my cards. First card I have is a jack, then a king, ace, and then finally a 5, and that means we must have the 2 left over. So that's another arrangement. So what were the chances that you could have guessed my arrangement or predicted my arrangement? And so what we're going to do is we're going to look at the math behind this. When you looked at the very first card, when you got ready to make the prediction of what it was, the chance that you could get it was a 1 out of 5 chance. There's 5 cards, you have 1 out of 5. Now let's say you got it right. Let's say you guessed jack. Well, that means the next card, there's only 4 left. you would have a 1 out of 4 chance. And this is going to continue. This is where it's like dependent probability. Next would be 1 out of 3. On your fourth pick, you have a 1.5 chance. If you get the first 4 right, you're going to get the fifth one right. So when we multiply all those together, the probability you could guess this would be 1 out of 120. Now let's say you just wanted to know the number of combinations, not the probability. Well, you could just multiply the 5 by the 4 by 3 by 2 by 1, and you get 120. So you can actually think of this 2 ways. You have a 1 out of 120 chance of correctly guessing the arrangement, or you could think of it as there's 120 different ways or 120 different combinations.